All right, everybody. Welcome to our new season of Discrete Optimization Talks, DOTS. The format is as usual. We have two 30-minute talks, well, 25-minute talks plus questions, and then we are going to have breakout rooms in an hour where you will have the opportunity to join and talk to the speakers in a more small number of people to one setting. And then we can also just stick around and socialize. So I hope you take advantage of that. Thank you, everybody, for coming. We start today with Selvaprabu Nadarajah, someone I know quite well for a long time. I would say I in some sense, the credit for my introduction to mixed integer programming comes from Selva's patience with me when I started out in this field. Selva is currently an associate professor of Information and Decision Sciences at the University of Illinois at Chicago College of Business. His research addresses challenges at the interface of operations and finance arising in the energy industry using reinforcement learning and optimization. His recent work develops self-adapting approaches, which are optimization methods and formulations that are capable of automatically adapting themselves to instance-specific information in a problem class or information arriving over time. Selva has received multiple awards, such as the 2021 Commodity and Energy Markets Association Best Paper Award, 2020 Inform's NRA Young Researcher Prize, Best Overall Paper at the 2020 in Europe's Workshop on Tackling Climate Change with Machine Learning, the 2014 William L. Cooper Dissertation Award, the 2013 Egon Balish Best Student Paper Award, and that's because he was at CMU, where he completed his PhD in operations research at the Tufts School of Business. With that, we welcome Selva to talk about his recent research.
All right. Can everyone hear me well? Good. All right. All right. Thanks, Alex. And so I'm looking forward to the research conversation today. So like Alex mentioned, so this specific paper is part of a broader research agenda to develop techniques and formulations that approximate large-scale MDPs, but with a specific focus and emphasis on the formulations techniques adapting to instance-specific structure and data, right? And so it's sort of it's nice to speak at a discrete optimization series because the motivation for this work comes from discrete optimization solvers, sort of a previous life of mine with which intersects with Alex. And so if you look at commercial solvers for discrete optimization, an important part of their success comes from pre-processing and adapting solution strategies to the solution progress they make on specific instances. So with that inspiration, we're trying to take some of those ideas and try to port them over to MDPs. So that's the backdrop of the talk. This specific paper is joint work with my close friend, Andre Cire, an amazing co-author, who I'm going to meet in a few hours. So I'm driving to Toronto after this talk. Okay, so with that said, what I'm going to do is present a weakly coupled MDPs with an example, and then I'll present network relaxations. So I'm going to use this multi-arm bandit problem. It's an example from Caro and Gallion in 2007. So the problem goes like this. There's a retailer that wants to sell J items, let's say 50 different types of laptops over 10 weeks, right? And every week, the retailer has to choose which subset of those laptops to show, actually put them on the shelf. So in this case, in week 1, there are 4 laptops that are shown. And the seller has a prior about the demand distribution for the laptops, but that's uncertain. And so if I show a particular laptop, I get to sample true demand, and then I can do a Bayesian update of my demand distribution for those products for the next time period and so on, right? So I do this for 10 weeks. So I'm looking at finite horizon discrete state action MDPs, right? And the objective is to show different sets of assortments to maximize expected profits. So that's the problem. This is a multi-arm bandit problem with demand learning in it, and the arms correspond to individual products. And you can think of pulling an arm as a binary action corresponding to a product. So let's take product 1 here. Product 1 has an action A1, and if it's equal to 1, I show that product, put it in the assortment. And the state of the MDP has the parameters of the demand distribution that I don't know. So in this case, let's say it's a gamma Poisson Bayesian process. So it has a shape and a rate parameter. That's the state. And these are discrete variables, right? And so if I choose A1 equals 1, so I put the product in the assortment, then I get a reward. And I update my parameters M1 and alpha 1 to M1 prime and alpha 1 prime. So that's the transition in the MDP. Okay. And so I have the same setup for every product. So there's an MDP per product. And the decision is whether I put the product in the assortment. Okay. Now, what makes this problem interesting and weakly coupled is that in every week, I can't show all the products at once. There are potentially shelf space constraints, which you can think of as a knapsack constraint. There could be cardinality constraints that limit the number of products I show every week. So these are called linking constraints in the weakly coupled MDP literature, right? So you can have one constraint or you can have multiple constraints. And what they do essentially, at a conceptual level, is they require these independent MDPs to coordinate the actions now. You can't just take actions independently, right? So that's essentially weakly coupled MDP through an example. So let me formalize this. So from the example, you can think of having capital J different component MDPs. So one for every product. The state for component 1 will be S subscript 1. The action for component 1 will be A subscript 1. It'll have its own action set and state set. Once I take an action, I get a reward. And I transition according to this probability kernel, which is to S prime 1 given S1 A1, and the whole process repeats. So I have J copies of such MDPs. I should take that back. It's not copies. J independent MDPs for each product. The key thing here is these MDPs are independent, right? So if I take an action in component 1, it doesn't really depend on the action in component 2. So the action sets are independent. The state transitions are also independent, and the rewards are independent, right? So the independent component MDPs. Now, if you're only interested in solving the problem for component 1, then you can cast that MDP as a stochastic dynamic program. So there's a standard stochastic DP formulation. V here is the value function that depends on the period, the component, and the state for that component alone. So in the example, we saw that it was the shape and rate parameter of the demand distribution. I take an action, receive the reward, and I transition to the next period, right? So throughout the talk, we'll assume that for a given component, its MDP is easy to solve. Okay, and that's typically the case. These are low-dimensional MDPs. You can solve them exactly. And so if you want to find the optimal policy for just one component, so in a product example, whether you show a product or not, that's easy problem. Okay, we can solve it and get the policy from these actions from the optimization. So far, no coupling, right? So what makes the weakly coupled MDP interesting is I take these component MDPs, add to that linking constraints. So the linking constraints that I've shown here are in a very general form, but for the purposes of this talk, you can think of it as something like a knapsack constraint where I have coefficients multiplied by component actions less than or equal to a constant. We do allow state dependence in general, but I think we can ignore it for this talk. Once you have these linking constraints in place, you can find a policy for the weakly coupled MDP problem, also using stochastic DP. So it's a stochastic DP that looks like this, but there are key differences. So in this stochastic DP, the value function depends on a state vector, where the state vector S has the components for every component-specific MDP, right? They're all coupled together. The action is also a vector. You have the component actions all string together. And the action set here looks almost the same as the previous case, but there's a key difference. Each of the component actions depend to their individual action sets, but now you have the linking constraint. Okay, so this is a high-dimensional MDP. The goal is to try to solve this stochastic DP, because not only do I get the value function, but if I solve the right-hand side with the exact value function, I actually get controls. Right? I get actions at every state. And the goal is to find a policy, which is a mapping between states to actions. Right? I want to find the optimal policy. And you don't necessarily have to do stochastic DP to find the optimal policy. There are other methods, right? But in today's talk, I'll focus on stochastic dynamic programming. And the difficulty of the challenge, the underlying challenge is I can't compute an optimal policy. Okay, so that's a starting point. But this has very specific structure, right? So the difficulty or coupling comes from these set of K constraints, linking constraints. So think of this as 2 or 3 knapsack constraints. So the natural thing to do would be, anyone, what would you do? If you had one set of constraints that create an issue, what would be a natural idea?
relax them.
Relax them, right? Lagrangian. So that's sort of the main idea in this literature. So you dualize the linking constraints just like we would do in deterministic optimization. So these are the k linking constraints. You assign dual variables lambda tk, and you dualize them. And then the MDP decouples again to component-specific MDPs, but not quite the original component MDPs that we saw. Now the reward is adjusted by a penalty that depends on the Lagrange multipliers and the coefficients of the linking constraints corresponding to that component, as you would expect. And so the value function here, I've superscripted by lambda just to indicate that this is given a penalty, right? But these are component level value functions for every component. Now, the goal was to find the optimal policy, which was hard to find. But the nice thing is if you can solve these component specific MDPs, which are low dimensional and easy to solve by assumption, the solution to it actually provides an upper bound on the optimal policy value that you don't know. So if you evaluate the component specific MDP at the initial state, S naught J is the state of component J at time 0. And then this is the adjustment for the right-hand side of the constraints. This sum for every feasible Lagrange multiplier gives you an upper bound on the optimal policy value. And so you can think of the Lagrangian dual as just minimizing over the Lagrange multipliers. Again, direct analog of what we would do in the deterministic case, right? And so this is the most popular approach for weakly coupled DPs. And once you have the solution to this Lagrangian dual, then you go ahead and you say, okay, I don't know the exact value function over this vector state, but I have this separable value function terms. If I want to estimate the value at a given state, I just sum the component value functions together, and then I get an approximation. I plug it into the right-hand side of the original MDP, and I can back out actions. So only thing I've done here is I've taken the original stochastic DP I showed you, which I cannot solve, right? So instead of the exact value function on the right-hand side, I plugged in the approximation I just computed. So now at every state, if I solve this optimization, I can get a feasible action. And this will define a policy, but not necessarily an optimal policy because this V hat is not exact. Okay? All right, so this gives us a nice framework or analog of deterministic optimization. I have an optimal policy value that I don't know. If I use the Lagrangian, I get an upper bound on the optimal policy value. I can use the value functions at the component level to construct a value function approximation, get a policy. It's a feasible policy, but not necessarily optimal. So if I simulate it, I'll get a lower bound, right? So I get an optimality gap. So that's the backdrop, right? So that's essentially background on weakly coupled DPs. Now, what do we do, right? So the literature solves Lagrangian largely. If you look at general purpose algorithms of weakly coupled DP, so it goes back to the late 80s by Whittle. It's a PhD thesis, which interestingly was not published, right? And then there was a paper by Edelman Masuro in 2008, which is a seminal paper that compares this approximate linear programming approach, which is a strengthening of the Lagrangian. So it provides upper bounds that are stronger than the Lagrangian, but the model, the linear programming model to get the value function approximation is high dimensional. So it's exponentially large in general, so it's hard to solve. And then recent work, there are a couple of papers by Bertsimas and Misick and Brown and Zhang that give conditions under which the stronger ALP approach is actually equivalent to the Lagrangian. This happens, for instance, for a multi-arm banded problem with a single cardinality constraint under mild conditions, right? So the consensus of the literature currently, let me summarize, is the following. If ALP and Lagrangian are equivalent, then solve Lagrangian, right? Why would you solve a larger model? The annoying thing is that if ALP is not equal to the Lagrangian, so if ALP can give you stronger approximations, you still solve the Lagrangian because you can't solve ALP, right? And so this bothered us a bit. And so we said, okay, let's try to find strengthening of the Lagrangian formulations that actually can be solved. Right? So that's sort of the motivation for this research. And we wanted to understand a little bit more about the Lagrangian and ALP before we set out on our approach. So let me sort of tell you how we think about Lagrangian and ALP. These are what we refer to as static LP approximations. So if you think about a WDP instance, they have linking constraints, right? So say 2 knapsack constraints, for instance, right? And there's also data in those knapsack constraints. So just because you're in the knapsack linking constraints class doesn't mean you know the difficulty of the instance, right? Depending on the coefficients, it could be knapsack constraints could be loose or tight. So it depends on both the linking constraints combinatorial structure and the actual data. these static LP approximations, the size of their approximations, if you think about them as linear programs, the number of variables and constraints is what we call size. It depends on how the linking constraints are posed in the initial formulation. So if you take Lagrangian, it depends on the number of linking constraints. You have one dual variable per linking constraint, right? It doesn't really depend on how difficult the constraint is. If you look at the approximate linear program, which I haven't shown you, trust me, it just enumerates all the feasible solutions to the linking constraints. Again, a static formulation. So our prior, when we started this work, was that perhaps the reason we can't improve on Lagrangian and get solvable models is because we're looking at static approximations, right? And so the solution and the main contribution to the paper is a self-adapting approximation, right? So conceptually, this is the way it works. So you have the linking constraints and the data, and we'll provide an LP formulation that's an approximation and gives you an approximation to the value function, where the number of variables and constraints depends on an assessment of the difficulty of the instance, where this assessment of difficulty depends on the combinatorial structure, so if it's knapsack, cardinality, or tree structure, what have you, and the specific data in the constraints, right? So we need both. And so for the rest of the talk, I'm going to tell you what that approximation is, how we do that, and then we'll go back to the motivation of model selection and ask, does this new model, the self-adapting approximation, does it actually make a difference in model selection? Will I ever use it? And then third, give you some computational assessment. Okay, so that's where we're going. Good. So the starting point is the Lagrangian. And here's the LP formulation of Lagrangian. This is from Whittle from the late 80s. So the variables of this Lagrangian reformulation are these Y variables. And you can interpret this Y variable, so YTJ, SJ, AJ, as the probability of reaching state SJ and taking action AJ at the jth component MDP. So it's like a frequency, right? The probability of reaching that state and taking action. The objective function of this LP is the reward multiplied by this Y variable summed up. So you can think about it as an expectation of the reward with respect to this distribution. Okay. There are two sets of constraints. The first set of constraints are probability transition laws. Let me open it up. So here, at the initial period, you send one flow of probability out, and there are another set of constraints that essentially ensure that you satisfy the transition probability law across time. Okay, so that's it. And there's a second set of constraints, which is what we're most interested in. This is where the linking constraints show up. And you can see you have the linking constraint coefficients here, but they're multiplied by Y. So what the Lagrangian essentially does is it takes an expectation of the linking constraints using this Y distribution that you're optimizing over, and so it essentially averages the linking constraints. Okay, so this is undesirable, somewhat expected, right? Because you would expect some sort of convexification when you do Lagrangian. So this we know from discrete optimization, but from an information sense, we're destroying the combinatorial structure. So there might be an opportunity here to strengthen the Lagrangian. So that's the simple idea behind the paper. So we take the original Lagrangian model, same objective, same flow constraints, but instead of these average linking constraints, we replace it by an exact flow representation of the linking constraints. Right? So let's not average it, let's represent it exactly. And so we call this class of relaxations feasibility network relaxations, because it depends on a network representation of the feasible solutions to the linking constraints. Right? So that's the key idea. Now, I still haven't told you why it's self-adapting, it's not clear. But let me first explain feasibility networks, and then I'll tell you why they adapt. Okay, so the first step of developing a network is to create one where parts of the network correspond to feasible solutions to the linking constraints. Right? There has to be a bijection between parts and solutions. Once you have such a network, then you can associate variables to the edges, constraints on the nodes, and use a linear system. Right? That's something that's standard that we use in optimization. We can do that. So let me illustrate this using an example. So going back to the multi-unbanded case I showed you, let's assume J equals three products. Remember, binary actions, AJ equals 1 means I put the product in the assortment, 0 means I don't, and we'll consider two knapsack linking constraints with the specific data. Okay. So here's an example of a feasibility network. So you can see it has 4 layers, 1, 2, 3, 4. The first layer corresponds to product 1. And the edges coming out of it are the 1 and 0 edges. So A1 equals 1, I put the product in. Dashed edge means I don't. All the edges coming out of layer 2 correspond to product 2. All edges coming out of layer 3 correspond to product 3. And the last one is the dummy edge, dummy node, sorry. Right? And if you look at a path here, so A1 equals 1, A2 equals 0, A3 equals 0, you can see it's feasible to both the knapsack constraints. Right? A1 equals 1, A2 equals 0, A3 equals 1 is also feasible. You won't see a path A1 equals 1, A2 equals 1, because if you set A1 and A2 equals 0, it'll violate the second constraint. So I'll ask you to trust me that there's a bijection between the paths here and the constraints and feasible solutions. But the first challenge here is that I haven't told you how I got this network, first of all, right? But this network is not unique. So let me show you another feasibility network where the same property holds. This network, the paths form a bijection to the feasible solutions of these knapsack constraints. And just visually, this is a bigger network, right? It has more nodes and edges than the previous one. I think you'd agree with me on that, right? Just visually, it's clear. So this is the slack network that you would construct in sort of in your first algorithms class, right? So algorithms 101, when you see a knapsack constraint, you have slack of each of these constraints in the nodes, and you track the slack till the end, right? And so using a general feasibility network will not give you a self-adapting formulation, because remember, the goal was to provide a formulation where the size represents difficulty. So for a given instance, if there's a large network and a small network, you need to find the smallest network, right? And so that's exactly what we do. We give a simple procedure, a merging procedure that starts with the slack network and finds a minimal network, and we show that that minimal network is in fact unique for every instance, right? So that's good. I'm not going to show you the merging procedure in the interest of time, but it's a simple merging procedure. Just move backwards and merge now. Okay, but that's good. So we have a minimal network and it's unique. So if I take a flow formulation of this minimal network and plug it into the LP I showed you, I'll have a notion of a minimal LP formulation that strengthens the Lagrangian. Okay, and so skip this. Okay, and that's the feasible network relaxation. To sort of summarize, same objective as the Lagrangian. First set of constraints, exactly the same. The only difference is this flow formulation of the feasibility network I showed you. So we introduced some new Z variables, one for every edge in the network I showed you, and a constraint, one for every node. And then there are constraints that tie the Y variables to the Z variables. The main thing to note is that the size of this formulation depends on the size of the feasibility network. And so when we have the minimal network in there, we get the smallest formulation. Okay, now why is it self-adapting? Let me illustrate that. So here's the example with the two knapsack constraints, and this is the minimal network that we just saw. Let me take the right-hand side 14 and 20 and just make them large, right? If I make them large, what's going to happen is all the actions are going to become feasible, right? They become redundant. So clearly it's an easier problem. And so if you look at the minimal network for these set of constraints, it's this. So you can see the number of nodes and edges decrease, right? And you can actually go the other way around. I'll show you in numerical experiments later. If you tighten the constraints, then again, you see that the network starts becoming smaller. And there's sort of a middle point, which is where it's hard. Okay, and so this adapts to both the combinatorial structure and the data. All right, so that's the approximation. Now, does it really solve the motivating issue with model selection? So let me show you some analysis here. So first, let's compare the feasibility network relaxation with the Lagrangian. First, an obvious result, right? So FNR, the upper bound should be stronger than the Lagrangian because the Lagrangian averages the linking constraints. We have an exact representation, so that just falls out immediately. We also give a TU condition on a matrix for which the FNR VFA and the Lagrangian VFA are exactly the same. This unintentionally generalizes a condition from the 2021 paper by Zhang and Brown, which is a great paper. I highly encourage you to read. But the reason we generalize it is because we take this network perspective, right? So that's why we can generalize it. And we have an example in the paper, which I don't have time to go through here. But what it shows is that if you take this feasibility network relaxation that's stronger than Lagrangian, the model size can actually be smaller than the Lagrangian. So you get a stronger approximation of smaller size, which is a nice example of why this adaptive formulations are helpful, right? You can actually get stronger approximations faster, and we'll see this in the numerical experiments. The construction is a bit tricky, so I won't get into it. So that's FNR versus Lagrangian. What about this approximate LP approach, which is the existing formulation in the literature that does better than Lagrangian, but we can't solve? It's an LP like this. The variables are the value function approximation. It's still separable. And the constraints depend on period, state, and action. Let me just say that the number of constraints here are the issue, right? So you can have potentially exponentially many constraints. So that's why we can't solve this model. But Edelman and Massaro showed that the ALP upper bound is stronger than the Lagrangian upper bound. Now I'm going to show you some newer results on this in terms of quality first, and then we'll go to model size. So in 2016, Bertsimas and Misick introduced a model called alt-lag, and they showed that the alt-lag value function approximation is equivalent to the ALP value function approximation, right? So same strength, different model. We show that our FNR value function approximation is also equivalent to the ALP VFA, right? So all different models to get the same thing. So you might ask, why do you care about FNR? Size matters, okay? And so now let's look at the model size. So here we compare the ratio between different model sizes, so variables plus constraints. So the first set of results are for ALP and FNR. So ALP model size divided by FNR model size. We have a lower bound of 1, which shows that the FNR model will be smaller than the ALP model under very mild conditions. So if you have 3 components and 2 states, at least 2 states per components, this will work, okay? So, and there's an upper bound here, which shows that the ALP can be substantially larger because you have a product of state action spaces, and this is a sum of state action spaces. We have a very similar result between the alt-lag and the FNR model, lower bound of 1 and an upper bound. Both these upper bounds can be achieved. We can give instances, these bounds are tight. And even more, we can give you a sequence of instances where these ratios become progressively bad and achieve that bound, right? So these are not unlikely bounds. Okay, so the theory suggests there is some hope, right? But it's still not clear whether model size is the right thing to look at, because we all know there could be smaller models that are harder to solve, right? So it's not clear yet. So let's look at the computational results. So the first class of instances are the knapsack multi-arm bandits. So the multi-arm bandit problems that I just showed you, we have small instances with 3 linking constraints, and we have large instances with between 1 and 5 linking constraints. The number of states in the large instances are 10 to the power 41. These are large problems, okay? Approximate linear program cannot even be loaded. So that's out of the question. So we compare the Lagrangian approach, the alt-lag from Bertsimas and Misick, and 2 versions of our formulation, the minimal model, a self-adapting FNR, and the FNR with a slack network. So first, let me show you the results on the small instances. So here on the y-axis, you have model size, variables plus constraints. On the x-axis, you have instances with different constraint ratios. Constraint ratio of 10 means very tight linking constraints, so few feasible solutions. Constraint ratio of 90 means constraints that have a lot of weak constraints, a lot of feasible solutions, but almost redundant. And you can see alt-lag, the orange line, the model size grows with the number of feasible solutions. Our FNR model with the slack network also grows, but at a slower rate. But the minimal model has different qualitative behavior from the other 2 models. It's easier to solve when the constraint ratio is really small or large, and the difficulties in between, which is what we expected, right? And so it's nice to see that actually happens. Let me show you upper bounds and policies, since I'm running out of time. The graphs show you upper bounds on the small instances, which is the left panel, and the right panel shows you large instances. The improvements in the upper bounds are substantial, somewhere between 5% to 60%. The number of constraints, linking constraints does matter, right? So if you have a lot of linking constraints and the constraints are tight, which is where we see the most improvement. If the linking constraints don't matter as much, the improvements are still significant, so 5%, but not as much as 60%. The policies between FNR and Lagrangian on these instances are essentially the same. Okay, and this is consistent with previous results on these applications as well. So one more application. So this is a preemptive maintenance application. This is from a telecom company that we got data from. So you have J different cell towers, and the deterioration of each tower is modeled by an MDP. The intervention or arm pull of one here corresponds to doing maintenance on the tower. The maintenance for the particular company we worked with was a software update. It's not physical maintenance, right? And the linking constraint is that you don't want to do a software update on towers that are really close together, because if the update fails and the towers go down at the same time, there'll be coverage issues, okay? So the linking constraints here are conflict graph constraints. And the main difference from the previous application is the number of linking constraints here can be large, depending on the edges of the conflict graph. That was 1 to 5, here can be large. Skip the slide. And let's look at model size behavior on small instances. We compare Lagrangian versus FNR. Here you see what I mentioned earlier, that the Lagrangian can actually be slower to solve than our model, because you have a lot of dual multipliers. Okay, on this case, that's the main observation of this slide. Now let's look at policies and bounds. So on the left panel, you have a bound comparison. And you can see that depending on the conflict ratio, which is again, the number of constraints essentially in an application, you see significant improvements to Lagrangian, right? It can be up to 70%. And the right panel shows the policy comparison. The red is Lagrangian optimality gaps. The blue is our model, the self-adapting FNR model, and the optimality gaps are substantially lower. So you can get significant improvements. How many minutes do I have, Alex?
0, -2.
Okay, I'm going to stop here. So let me just say that the main point I want to get across is that the self-adapting formulations provide a proportionate response to the difficulty of the instance, right? And the main actionable takeaway, which we were bothered by, if ALP is equivalent to Lagrangian, you solve Lagrangian. I think that's a good rule of thumb, although there are exceptions, like I mentioned. But if ALP is not equal to Lagrangian, now we have a model that you can actually solve, right? And if it's too hard to solve a model, which is always possible, then you go back to Lagrangian. Right? So the paper got accepted in Management Sciences a few days ago, and it's part of a broader push towards self-adapting RL and optimization. There's a lot of wonderful authors working on it, and I'm happy to talk about it in the breakout session. Thank you.
Thank you, Selva. I think in the interest of time, I guess the questions will all be saved for the breakout rooms. So please stick around for those for anybody who has questions. I congratulate you on the management science acceptance, and I love this little, the line, putting everyone between continuous and discrete based on their research.
But I have a PhD student who's at UChicago who's sort of transitioning. He does both.
Yeah. This is fantastic. All right. Thank you so much, Selva. I'll stop the recording now.